All right, today we're going to talk, hopefully finish off what we're doing in full factorial stuff. So try to finish off the analysis, or at least the main part of the analysis. And we left off here, and so last time Thomas brought up a good point. So we talked about how to calculate an interaction, right? We said for an x1, x2 interaction, it was the x1 effect at the high value of x2 minus the x1 effect at the low value of x2, and 1/2 that difference was our definition of an interaction. And so we looked at this interaction plot, and we made one of these for that example, right? So it was y, the response, versus x1. And so if you think about, we did it this way in class, but if it's an x1, x2 interaction, then the choice of this plot, y1 versus x1, is fairly arbitrary. Why not y1 versus x2? And so what this plot is getting at is just saying, no matter what variable you pick, x1 and make your interaction plot, or x2 and make your interaction plot, when you go through the calculation, you get the same equation both times, either way, I should say. So when you're looking at, hey, I have an arbitrary choice, which one does it pick? The answer is it doesn't matter, which is what you'd hope would be the answer if all things were as they're supposed to be. So if you're wondering, if you had that question, is I could have picked x1, I could have picked x2 for this interaction plot, it doesn't really matter. So again, keep in mind that definition of words, in words though, for the interaction. So 1/2 the difference of the effect of x1 at a high value of x2, and the effect of x1 at a low value of x2. And you could swap x1 and x2 around in that wording and still have the same answer, still the same value for the interaction effect. So we talked about main effects, which is on average what's x1 doing, what's x2 doing, as far as what's the change in the response y as x1 goes from its low to its high value. And now we have the interaction effects, which are the effect of x1 depends on x2, and so forth. Okay, so before we get into the analysis, just some rather mundane stuff is we have 2 to the k designs. So our designs come in these packets of 2, 4, 8, 16, 32 runs, and they are coded with the high value and the low value and the high value of each factor. And how do you construct the design table of number of experiments? For example, if you had a 2 to the 4th design, that would look like this. You have 4 factors, and the high and low values of each variable are in that table. And how do you keep track to make sure you got all of them? You just start alternating -1, +1 in this column. Then you do 2 minuses 2 plus, then 4, then 8. You keep doing that, and that's a methodical way and the standard way of getting these 2 to the k designs written down. Does that make sense? And if you pick that row, what is that row saying? When it says plus for x1, plus for x2, what does that mean? This row represents what? What are we going to do with this row? Pardon? Plot a data point. But so this row represents, we have these y values here, right? That row represents a particular experiment. So that means we did an experiment, we got some value in the response, and these represent what? These pluses and minuses. Right, the settings of these factors, x1, x2, and so forth, and they're the high values and low values. Somewhere else we have to define a high value is whatever, 10 psig, or a high value is 300k, whatever those actual values are that someone is going to set that factor at to run the experiment. that make sense? Again, don't want to get too far away from actually doing experiments. So that's how you just write down these designs. Now, how do we compute? I mentioned before, we're going to use Excel to calculate all the effects. So this stuff right here, it's called the design table. It is, what experiments are you going to run? We're going to flesh it out. So here is a design table right here. We'll talk about that mean column later. But we have 4 runs, and here are the high and low values of x1 and x2. Right? A two square to design. We have 4 runs, and all possible combinations of high and low levels of all the factors. There are only 2 factors in this case. Gives 4 runs. So we get y values out here. So we get a number here, 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 and here. And when we calculated the main effect, say, of x1, we said here's the high value of x1. We said let's add the 2 high values of x1. And then we found those are the low values of x1. And we add the high values, subtract off the low values, and divide by 2 in this case. So we have 2 estimates of the x1 effect, and we average them together. Does that make sense? You ever see how that comes from this? Maybe I'll make this a little bit more explicit. So this would be y1, y2, y3, y4. So y4 plus y2 minus y1 minus y3 over 2. So that's how we calculate the main effect of x1. For x2, what do? We look at the x2 column and say, well, y3 and y4 are at the high value. So we add those. Then y1 and y2 are at the low value. So we subtract those off and then divide by 2. Right? So every time we're calculating these effects, we're just looking at wherever that effect is at its high value, that comes in positive. The low value comes in negative, and then we sum them all up. The highs, that's the same as the average of the highs minus the average of the lows after we've divided by 2 there. Okay, and so I think we did as much when we looked at that example, that cube plot. So then for interactions, we can use that definition, which is kind of clunky. We could say, what's the x1 effect at a high value of x2, and so forth. And it gets a little hard to compute that every time. Now, don't forget that definition. It's important to know it. But as far as being efficient and fast anyway at calculating these effects out, there's a nice way of doing this in Excel. And so that's this. So again, the design table, the experiments we do are here. But we can add to it. We can add extra columns in the computation table. So these are some extra, write it out, columns that we're using just to help us calculate effects. And so for this column that we're going to use to calculate the x1, x2 interaction, how we get these values is we're just going to multiply these 2 values together. Imagine these are -1s and +1s in Excel, and not just minuses and pluses. So if I take -1 times a -1, I get a +1. Right? Plus minus gives me negative, and so forth. So you multiply these 2 things together, and that gives you that column. Is everyone okay with how we get that column? Okay, just multiply the components of that column together. And now, when we want to calculate this interaction, I'll have to rewrite these things. We just say, okay, we find where the high values are. So the 1-2 interaction would be y4 plus y1. And then here are the low values. We're going to subtract those off. Minus y2 minus 3 over 2. So by looking at that column, it tells us which values of y we add and subtract in order to get that effect. So that will give us a number for the interaction effect. And it's on the same order, the same scale as the main effects, so that we can compare. Does anyone have questions about calculating that interaction? So it's really nice when we have this column in the computation table, we can very easily calculate this, calculate that interaction. Okay. So now a 2 cube design, 2 to the 3 design, has 3 factors. So how many runs do we have? If we just did a single run at each condition, 2 to the 3 design, it's kind of the answers here. 8 runs. So that's our whole experiment right there. All possible combinations of high and low of those 3 factors. You remember, each row is 1 run. But now the computation table has the 2-way interactions. There's 3 possibilities there, and then 1 3-way interaction. And just take a minute and convince yourself, for example, the x1, x3 column, you get these values by multiplying this x1 column by the corresponding elements of the x3 column. Does everyone see that? And the 1, 2, 3 column is, if I multiply all 3 things together, that's negative, that's positive, and so forth. And keep in mind, at the end of it, we have data. And we can look to the positive and negative values in our computation table to figure out what we need to do by adding and subtracting the y's. So we're going to add and subtract y's and divide by how much? Last time we divided by 2. How much do we divide by in this case? 4. That's right. Ends up being half the number of runs, right? So we have 4 estimates of each effect or each interaction. And we're averaging them together. And we can go even further, a 2 to the 4th design. Now things get a little bit more fun. Here are the experiments we did. Here are all possible 2-way interactions, 3-way interactions, and 1 4-way interaction. When you get to the 2 to the 5th design, it can be hard to keep track of all the interactions. So that's where we learn that combinations. So you can think of, how many of these do I have? Well, I have 4 factors, choose 2, 4, choose 3, 4, choose 4. Remember that? Way back from chapter 2, chapter 3. That can tell you how many of these things you have and if you're missing some of those. Okay, one thing to really be careful about is think about what are the things that we set in the experiment. Do we set, say, do I set this value of the x1, x4 interaction? Can I set the x1, x4 interaction in an experiment? No. What can I set that would give me this value for an x1, x4 interaction? x1 and x4. So that's a common mistake. So these are the variables that we have. We only have 4 variables that we can go in there and dial in and set to some level. Once you set these, then these interactions are determined from that. Okay, so you can't go and set the 1 4 interaction. So often in this next exam, I will ask you a question like, here's a set of data, what effects are significant, and tell me the optimum settings. And invariably, I'll get people that will say, put x1 at the high value, x3 at the low value, and put the x1, x3 interaction at the high value. Okay, you can't set the interaction, right? You can only set the factors. Right? Again, think of an experiment. These are things like temperature, pressure, concentration, some sort of mass or force, something that you can set in the experiment. Right? That's what the factors are. That's the only thing that we can set. And then all of this is calculated from that. Might as well talk about this now. When you're doing degrees of freedom analysis, what do? You remember degrees of freedom analysis? Anyone done that? Nobody? Really? You've heard the thing, degrees of freedom analysis? Okay, so you're doing a problem, and it says do a degrees of freedom analysis. You're usually comparing what two things? It's like a homework problem. I'm thinking just a regular homework problem, not an experiment yet. We'll get to the experiment later. Not a statistics homework problem. Think of a statics homework problem. A statics homework problem, and degrees of freedom analysis, what will it tell you when you're all done with it? Vaughn. Right. Right. So if you're wondering, can I solve this problem, you look at how many unknowns do you have and how many equations you have to get those unknowns, right? And if those are equal to each other, you can solve the problem. If you have more equations than unknowns, it's probably overspecified. If you have more unknowns than equations, then you can't solve it without assuming some value for an unknown. Okay, so that analogy is going to fall a little flat because this is similar to that. So when you're dealing with data, you can think of each data point like an equation. If I have a data point, I can calculate something from it. Remember, degrees of freedom was something we talked about when we talked about S, right? You know, how many things can I independently set? And we said, when we talked about S and we divided by n minus 1, it was because we burned up a degree of freedom in calculating the mean. We took our equations, if you will, our data points, and we calculated one thing, so it took away a degree of freedom. So we have 16 runs, which means we have, if you will, 16 degrees of freedom, or 16 things we can calculate. So we have, how many of these guys do we have? 4 of these, 6 of those, 4 of those, 1 of those. We have 15, we have 4 main effects, 6 two-way interactions, 4 three-way interactions, 1 four-way interaction, and then we can also calculate the average of all the points. Obviously mean, the average of all the points, that's going to be part of our model. So we can calculate 16 numbers, a mean and 15 effects out of our 16 data points. If we do that, we have used up all degrees of freedom in this experiment. So that means we have 0 degrees of freedom left to calculate noise, which is too bad because we really want to get a handle on noise as well. So one thing we might do is take this whole experiment and replicate it, which means we do each experiment twice. So if we did that, we would have 32 degrees of freedom total in 32 experiments. We'd use 16 calculating stuff, and then we'd have 16 other degrees of freedom that would go into our estimate of the noise. Yeah, Jack.
So if you only wanted 15 degrees of freedom out of this, you could calculate the noise?
Good question. We'll look at techniques in calculating less than these 16 things, and we'll use some of these things to estimate noise. But I'm kind of getting ahead of it if we go down that path. Yeah? Yeah, the mean is just you have 16 y's and it's the average of those.
So all those pluses are the same.
Yes. Why this column is here, it's not obvious yet. It's just going to be an easy way for us to calculate the mean once we get into our analysis. Good question. That is not obvious. All right, so a little bit too far ahead of this before actually getting into calculating stuff. So I want to get into there, and then I think we can circle back, and a lot of this stuff will make more sense, even this randomization stuff. So remind me, I need to get back here. This is really important stuff, but I think we ought to jump ahead one page in order for us to really figure out what's going on. So here's a real example. This is a 2 to the 3rd factorial experiment, and we're going to see this tired example over and over and over again. So we're doing reaction stuff, and we're varying temperature, pressure, residence time, and we have low values and we have high values. So 80 degrees, that's the low value. 120 is the high value for temperature. And then for pressure and residence time, or reaction time, if it's a batch reactor, so how long we let the reaction go before we quench it and measure what's there. So we set up a 2 to the 3rd design. So this is the design table right there. Those are the runs we did. So 8 unique experiments, and each of these experiments, each experiment we did 3 times. So we would say, sometimes we'll say R for 3 replicates. So the total number of runs is 24. Did that math in my head. It's kind of impressive. All right, so we did 24 total runs. Each experimental condition, we have 3 replicates. And we measured the reaction yield. So these are the responses. Or this is the response. Y, it's reaction yield, but the fact that Y is the same letter as yield starts with is just a coincidence. Okay, so we have, everyone understand what we're doing here? Just please ask questions if you don't get that part, because everything builds off that. So now, we did these, this is the design table. We can do the calculation table, which is going to help us calculate the interactions. We have a couple three two-way interactions, 1 3-way interaction, and we get each. So for example, we got this value here by multiplying temperature and residence time together. -1 times -1 is +1, and so forth. So does everyone know how we get these values for -1s and 1s? Okay. So then what we said we were going to do is, it's easiest if we take each of these measurements and calculate an average yield from it. And now we're going to look at this table and say every time, for example, if I wanted to calculate the effect of the main effect of R, I would say these 4 values, which are those 4, minus those 4 divided by 4 would give me the, so I would say y8 plus y7, I'll write it down, y5 minus y4 plus y. I'll distribute that negative sign, which will make it a little bit easier. I think you guys are all okay with that. Get rid of that parentheses, I don't need it. Okay, is everyone by that that's the main effect of residence time? Yeah, John.
So you said 24 total runs.
Yeah.
So take our just.
Oh yeah.
Is that still 4?
Yeah, great question. So we have 24 total runs. Why are we still dividing by 4? It's because I've taken the average of these 3, and so I'm using the average column here, and which is what we'll do always. We'll learn about later how you can just list all these 24 runs all the way down and do it that way. That's actually how Minitab prefers it. But for right now, good question. And I'll just say by taking the average, we're still looking at the average of the numbers we said we still have 4 estimates of whether these averages go from high to low. Morgan.
Where are you getting your yield?
Okay, where do these numbers come from? That was data. So we went in the experiment, went in the lab, we did this experiment, and it's just presented to you as the results of this example. Good. Any other questions? And everyone okay with this? Okay. So remember before when we talked about how vectors, we could recognize this as vectors. See the top part of this equation? And see if we took this column right here and we said this R column, if this was a vector, and if our Y bar column was a vector, and we took the dot product, we'd get the top of this. We'd get the numerator. Okay. So if I could, what I just said is, if I could take this as a vector and dotted it into that, I would get this. And so, does everyone see that part? If we recognize that, then that's going to be pretty straightforward, because in Excel, if we found that function, that'll do the dot product, we could type it in, say, at the bottom of the column and say, OK, dot that column into this one, and that will give me the numerator. I divide by 4, and I've got the effect. So that's called, oh, I should have asked if anyone's ever used it, sum product. And then you just highlight the columns. Might want to put an equal sign in there for Excel. That's the function in Excel that will give you the top, give you the numerator of what you want. You divide by 4, and then you've got the effect. And now we can do that at the bottom of each of these columns, and we'll have values for effects. So that's what I did here. There's the sum product formula. It's right there. And there are the effects. I just took this, divided that by 4, divided that by 4 to get the effect. Yeah, 2 questions at once.
So, okay, where did the sum product come from? Was that just the numerator of that equation?
Yes, the sum product is that function I typed into Excel. And what it did, for this one right here, I said sum product. I highlighted this column. Then I put a comma, and then highlighted average yield, which was that Y bar from before. And it returned this, which is the numerator in the effect calculation. So then I took this, divided by 4 to get that effect. And that is the effect we've been talking about. So in words, it's saying when we change temperature from, what was it? What was the low? 20 degrees to 120? Well, who's got that? 80 to 120. When we increase temperature from 80 to 120 degrees, our yield, on average, increased by 21.5, whatever units that was, probably percent. Right. So right here, when I increased pressure from whatever it was to whatever it was, low to high value, the yield only increased by 1. So not a big jump, right? Okay, before we start, those are what the effects are. Notice one thing. There's one little tricky part. To get the mean, what do I want to do? I want to add up all these numbers and divide by 8, right? So just because I've already got the sum product typed in, I'm just going to divide that one by 8 instead of 4 to get the mean. So this mean is just, that column there just gives us a bit of an easy way to calculate. That's the average of all the data. The mean yield was about 50 for all the data points. Okay, here's Excel. I've got this very thing on Excel that I did previously. So that's that. Let's just get rid of this. So what you do is here, if I can type right, there's some product, and then I want to highlight this, hit column or comma, I want to highlight this, then what do I want to do next? Because I'm going to copy it over to the right, I want to think through this, so I want to do that, right? Dollar signs. Everyone use dollar signs? All right. And you use F4, you don't put them in manually, right? Okay. Okay. So that's that. Copy it over, the dollar signs keep the average yield the same and give me the right column. I guess, anyone not use dollar signs in Excel ever? Oh, okay. What do they mean? What do they do? Okay, you're not using Excel. If I know I've got these two things and I'm going to copy this thing over here, I don't want, and for this I want the column to stay the same, right? So I'm going to put a dollar sign in front of that column, M, and it'll keep it the same. So then when I copied it over here, this didn't change. So this one did, because it wasn't dollar sign, this one didn't. So when you hit F4, it cycles through putting dollar signs in between the column and in the row and both. In this case, I didn't need it in front of the number, but it doesn't hurt, so I left it. But sometimes you only want it, if you put it in front of the number, then it'll keep the row constant when you copy down. All right, so anyway, that's Excel thing. Definitely learn that because you don't want to use Excel at all if you don't know how to do that because it'll just be frustrating. So there's all of these fun things in Excel. Oops, that's not escape. There we go. Okay, so that's how I got the sum product. Then I just did that divided by 4. Those are the effects. And I might as well, and then this one I have to divide by 8. And so we get those values that way. So that's the mean, but these guys right there, those are the effects. The average temperature effect, pressure effect, residence time, and then the interaction effect. Yeah, Thomas.
So let's say you wanted to maximize the yield. Would you just kind of confuse how the second and third interactions work in that respect?
Okay.
Let's say the pressure and the P dot R and the highest effect.
Oh, okay, great.
So that works as far as to maximize.
Okay, great. That's a great question. Let's explore all that and more. Let's look at, okay, so what do we do with this? We've got effects. We want to know a couple things. Thomas has the real take-home message is if we're trying to maximize the yield, what do we set temperature, pressure, and residence time at? So let's go through this. This temperature effect says we should run at high or low temperature to maximize yield. High temperature. Pressure would say what? All right, so the pain look on your face that many of you gave me says, I'm interpreting here, that I don't know if this is real. It's so small, is it noise or is it real? Is that the pained look or is it, I've already been here for 35 minutes and there's lots more minutes to go. Can't be that. Okay, so let's back up a step then. Before we start saying where we're going to optimize it, the question that we have to answer in statistics is, these are the signals. And which ones can be explained by noise and which ones can't be? we did 3 replicates, and the reason we did that was to get a handle on the noise, right? So before we go any further, we have to sort this out. We have to figure out which ones are real signals, which ones can be explained by noise. So if you had to just guess, you'd probably say the temperature effect looks real, right? The pressure residence time interaction looks real. Maybe this residence time main effect looks real. And this is, why is it negative? What does that mean? When you increase residence time, what happens to yield? It goes down. That's why it's negative. Yeah? Well, you can't really use process of elimination because they could all be noise. They could all be explained by noise. And that happens a lot more times than I think engineers would like to admit. You do an experiment and you find nothing. And that's that whole power deal that we talked about before. So we're not exactly sure. What we're doing is we're kind of comparing these to the other ones, and you could think of, oh, we haven't done Pareto charts, but what we're doing sort of visually is reasonable to pick. Those 3 things are much bigger than the other ones, but at some point you're going to get numbers that you're not exactly sure. Is this really significant? Is it not? What we need to do is get a formal statistical test to figure this out. And so let's think about this. This dovetails exactly with what we've done in hypothesis testing. We're going to set up a hypothesis test that says the mean of mu of this temperature effect is 0. The alternate hypothesis is that it's not 0. Then we're going to calculate a statistic, look at a rejection region, and do this hypothesis test on this. Then we'll do it here, 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 here. But we're going to do it all sort of very quickly in one Excel function copied over. But that's what we have to do. We have to do these hypotheses tests. We have to test the mu of this effect is 0, or the mu of that effect is not 0. And we're going to do that for each one of these. So then we're going to have what T is going to be the effect minus the hypothesized value divided by, this is where we talked about it before, right? So our T statistic is, what's the thing we're trying to talk about? It's an effect. Minus the hypothesized value, which is 0, divided by the noise in the effect. So that's where we're at now. We need to figure out, okay, how do we get this? What is the noise of this thing, this effect? And to do that, we need to think through, well, what is an effect? We just calculated it from individual data points. What did we do to calculate it? Is it a mean? Is it a difference between 2 means? What is it? And then we can build up the right noise for this. It's not the noise of the individual data points, right? It's the noise of the effect. Yeah, Derek, you had a question.
Is this by chance actual data, or is it just from a book problem?
It's from a book problem, but if they got it from actual data, I don't know.
I was just curious because like T has a pretty large effect and P and R don't, then TP and TR seem to have low effect and PR has
Oh, that's a great question. That's what we're talking about. Say that louder so everyone can hear you.
I was just curious why T had such a large effect by itself while P and R didn't, and then TP and TR had no effect while PR had a very large one.
Okay, does everyone hear that? Derek's wondering, with real, okay. So he's wondering, why does temperature have such a big effect? Residence time, pretty big effect, but this P and R have a huge effect, even though P had a small effect. Is that what your question was? Okay. Okay, it's related. Maybe we can get back to your exact question. Pardon? And it has a bigger, and this is actually a bigger effect than a main effect. Than TR. Okay, so, all right, so let's handle that question first. The interaction effects can be anything. As far as, all this is saying is that these two factors affect each other. So a low value for T and R is saying temperature is independent of residence time. So my optimum setting of temperature, it doesn't matter what residence time I set it at. Those two things act independently. I'll say it sharper than that. Their effect on the reaction yield is a separate independent effect. So temperature has an effect, maybe. Residence time has an effect, but they don't depend on each other. So the settings of temperature doesn't depend on the settings of residence time. Temperature is doing its thing, and separately residence time is doing its thing. That's what that small value is saying. Now what this is saying is, well, pressure and residence time are related. That means that if I asked you, what's the best pressure to run, your answer has to be, it depends on the residence time. And you could reverse that the same way. But another question could be, is why do we have such a big interaction when the main effect of pressure is small? And so that cycles back to something we're going to repeat very often is when you're interpreting this data, once you see a big interaction effect, and let's assume we prove this to be statistically significant. If that is significant, then you don't even really pay much attention to those main effects. I shouldn't really cross them out. We're still going to put them in our model, but we don't interpret the main effects because there's so much more to the story for pressure and residence time. So what it's saying is you can't explain pressure without talking about residence time. You can't explain residence time without talking about pressure. All right, so getting a bit ahead of myself there, but good questions. So now let's look at doing this hypothesis test. So we're going to have to calculate a T statistic, and to get that, we're going to need the noise of the effect. So I'll get back to your notes, and let's start thinking about that. So maybe we'll go off here. So the effect. What is an effect? To calculate effect, what did we do? We took all the average of all the high values minus the average of all the low values. So the effect of x1, we took the average of the high values. So effect of x1 maybe. Minus the average of the low values. So x1 was temperature. So we did this one, it's every other one. So I took the average of those four numbers minus the average of the three numbers that I didn't circle. So it was the difference between two averages. Is everyone okay with that? So now what we want is the noise in the effect. So let's look at the variance of, I'll call it E1 now. So that's going to be the noise of x1 equal of that. So sigma squared, square root of n, 1. All right, so I just don't want to miss something here. Bar plus. So the noise is going to be the noise of this y bar minus the noise of that y bar. And let's relate it to the noise of individual measurements. Remember the central limit theorem? So this would be sigma squared of the individual measurements divided by, I'm calling this N1. It's the number of data points that went into this average. And 2, the number of data points that went into that average. And I got a square root sign in there. which should be.
Is it plus or minus to the points?
Oh, it is plus. Thanks. Does that make sense why it's plus? Remember the minus 1 is squared with c squared and sigma squared back from chapter 2. Okay, is everyone okay with this? That's the noise and the difference between, the variance of the difference between two means, right? And so then if I want to just sigma, take the square root of all that. So square root of sigma squared n1 squared over n2. If these two sigma squareds, these are the individual measurements, if they're the same at the high and low values, which we're always going to assume is the case, then we can pull that out front and just call it sigma. So we're saying the noise at the high level of the effect is the same as the noise at the low level of the effect. We'll make that as something, the noise is constant throughout the experiment. So I just pulled that out front and took the square root. Is everyone okay there? And now 1 over n1 plus 1 over n2, that's okay. So in these experiments, however many experiments we do, half of them go into the high value and half are at the low value, right? So this would be 1/2 the total number of experiments, and I'm going to call that n sub f. Which the f means these factorial points. We're going to add some other points a little bit later, but these, for now, just think of those f's as that's the total number of points that we have. So sigma, that's going to be, so that 1/2 ends up 2 and 2 there. 2 plus 2 is 4. Last thing, I'm going to estimate, I'm not going to know sigma, I'll know S, and it'll be a pooled standard deviation like we pooled it before. So we are going to estimate sigma E. We'll just say, we'll call that SE. We kind of, sigma is the population parameter. We estimate it with what we know is from our data. SE, so these are the standard deviation of the effects. We can get those from the standard deviation of individual measurements. So that's the standard deviation of the effects, which are differences between two means. SP, that's the standard deviation of individual measurements. Remember before I said we're always going to try to match up the noise we're using with the thing we're trying to calculate. So that's why we're after SE. And we always build that up. It's always based upon the noise of the individual measurements. So there it is, SP. So that's where SE relates to SP for these factorial designs. And it's just a derivation of a difference between two means. So we know how many data points we have. If we get a pooled variance, assuming that the noise is the same at each data point, then we've got the noise and the effects, and now we can do that hypothesis test we talked about before. So, questions so far? So now, saying we're doing this hypothesis test, we figured out how do we get SE. We need NF, total number of experiments. That's 24, not 8. It's 24. And then the next thing we need is we need that SP. So maybe I'll go through the notes to blah, blah. I'm trying to look at where I've calculated that. Maybe I'll just do that in Excel. All right. I'll get rid of this stuff. Okay, I'll leave that there. So think about SP. What is it? It is the error in the individual measurements. How do we get that? We have, for each run, we have 3 replicates, right? So think about before. If I gave you 3 data points, you could calculate a mean from that, and you could calculate a standard deviation, right? And when we're doing hypothesis tests, where you're doing the difference between 2 means, if I had 3 data points here, 3 data points here, you calculate a standard deviation here, and then you could pool them together, weighting it with degrees of freedom from the last exam, right? So now we're doing the exact same thing, only instead of 2 sets, we have 8, right? I have 8 sets of 3. I have 3 data points here, 3 here, 3 here. I'm going to take those 8 groups of 3, calculate a standard deviation for each one of them, and then pool it together, and I'll use degrees of freedom as the weighting factor. So those 3 points, I can calculate an average. And I can calculate, instead of the standard deviation, I can calculate the variance. In Excel, it's VAR, right? How do we calculate that? That's 61.4 minus 59 squared plus 58.6 minus 59 squared, so forth, divided by 2. Okay, that's variance calculation. I can calculate that for each run. And then I have 8 estimates of S. And I'm going to pool them all together to get 1. So I'm going to take those and combine them to get 1 estimate of the variance. So what I really need to do is, if I had degrees of freedom, there's 2 degrees of freedom there, and there, and there, and there, and there, and there, and there. So I take that times that, divided by total degrees of freedom, and that gives me the variance. Should I write that down? So how we got this? So SP squared is going to be 4.9 times 2 plus, what's the rest? 1.2 times 2, on and on and on, down to 5.0 times 2 divided by 16. And that gives me 10.9. So keep in mind, it's the same exact thing that we did earlier in chapter 6 and in chapter 5. When we had 2 data points and we said variances are equal, we pooled them. We're doing the same thing, only we just have more than 2 sets. We have, instead of 2 estimates of S, or SP squared, or S squared, we have 8 in this case. If we had 16 runs, we'd have 16 of them. And we're gonna weight these, just like before. The weighting factor is what's degrees of freedom. This degrees of freedom is how many degrees of freedom went into the calculation of the noise. So 3 data points, we burn up 1 with the average. There's 2 degrees of freedom in that, in 4.9. There's 2 degrees of freedom that went into that estimation of the noise, and so forth. So SP squared is 10.9. You take the square root of that. That gives us SP, which is 3.3. And then we already said SE was 2SP over the square root of NF, which is 24 in this case. And so that gives us 1.35. Let me. Any questions on how we got to there? Feels like we're going kind of fast. Hankering for a group problem real soon. Let's see here. Yeah, we'll get a group problem here pretty soon. But I think I'm going a little bit too fast without one. All right. So if we go back to the notes, this is what I did all in that Excel spreadsheet. Almost all of that. We did all this, and we did all of this. For right now, ignore this column. That's later. So now, that's the noise of these guys right here. Right? These are effects. This is the noise of the effect. To calculate, to do that hypothesis test, we wanted t minus 0 over SE. I'm sorry, E. So for this t-value, you take E, which is 21.5, divided by SE, which is 1.35, and you get 15.9. So that is the t statistic associated with this test, which is the mean of the effect of temperature is 0. And the mean of the effect of temperature is not 0. So you assume the mean is 0, and then you calculate a t-value, and you are over here 15 standard deviations from the mean, almost 16 standard deviations from the mean. And we're going to compare it to, we could get a p-value from it, or we could get a t star. Right, so if we calculated a hurdle value for t that had an alpha of 5%, we could compare all these values to the hurdle value. So the hurdle value is, in this case, 2.12. And then each one of these that is bigger, larger, greater than 2.12. For the blue ones that I've circled, we have rejected the null hypothesis and accepted the alternative hypothesis. For this one, we're saying the null hypothesis that this mean is 0 or temperature is doing nothing, we reject it and say temperature is doing something. We see what this residence time is doing something, and the pressure residence time interaction is also significant, and we'll say real, doing something. All the other ones, we failed to reject the null hypothesis. So what we will say is our experiment showed that showed no evidence that these things are doing anything other than just, well, they are not doing anything. And the values that we get here are just reflecting the noise in the experiments. So we would go forward with, these are the 3 effects, the 3 out of the 7 possible effects that really are doing something. And now we will take that next step of, all right, let's interpret these effects and figure out what do we set temperature, pressure, and residence time at to maximize this yield. So we can make some plots for it. So this is a Pareto chart. A Pareto chart is just, these are the size of the effects, and they're ordered from greatest to least. And there's our hurdle value, and you say, okay, those are big. Right? So that Pareto charts are great for people without scientific background, because then it's very clear these things are big, and they're much bigger than those things that are small. So there's a cube plot, which gives us more information. We've looked at that before. And then Minitab also gives you all the interaction plots. So remember, interaction plots are showing us where we have These lines are fairly parallel, meaning no interaction between temperature, pressure, temperature, time. But the pressure residence time, those two slopes are nowhere near parallel. That was the significant reaction that we found. And it's telling us, wow, this is a pretty crazy thing. When you change pressure, time does the opposite thing. At one pressure, time does one thing. When you increase the pressure to the other side, then it's reversed. That's why those things cross. So I'm trying to get to something. Okay, any questions on that? All right, see if you can, without looking, let's just kind of go back here. And so, kind of without looking at the values, let me see some things here. Let me just close that down. Don't save that. Don't do that either. All right. Let's see if I can just pull up another. I want to get you guys doing something instead of me just talking the whole time. So what I want you to do is, let's get rid of that, and let's get rid of that, and let's change some data here. Let's do this. Okay, so messed with all the data. What I want you to do, calculate the effective residence time, and then calculate the noise and do this hypothesis test given what's up here. So I'll try to zoom in so you can see it. So first thing, let's calculate what's the effective residence time. You see all those things okay? Let's get rid of that one. So do these things right here. First one's this box. Clean that up a little bit. All right, if you have, I'm guessing you have questions, so raise your hand. Don't be sitting there stuck. Talk to people around you. We covered a lot of stuff today. All right, Katie, question. Pardon? Yeah, I got rid of the zeals, didn't I? All right, but that'll be later. Oh, you're already there? Okay, I'll bring him back. I'm just trying to clean it up a little bit. that better? Is that what you need? Okay, good. Yeah, check. Oh, good for you.
I take
HP is great.
I take the S right when it does this, not the sigma.
Yeah, I don't know that one. My guess is sigma would be the sum of squares divided by n instead of n minus 1. That's my guess. So you probably want the S.
Okay.
So just double check. Oh, is that the prime? Is that what it is then?
Yeah, the prime.
Ah, okay. How do you like it?
I like it a lot. The really cool thing I was doing is it can, if you go into the computer algebra, it can do like integrals with, it can do integrals with, well, you can have equations in the limits, and it will even do that.
Oh, yeah, instead of
So
just
it's
numbers.
helping me in my E&M class.
Cool. Now, you can use
Triple integrals.
and it does the RPN mode like all the other HPs, right?
It does, yeah. I just,
Have you done that, or do you?
that's what I've been using.
Oh,
I've
it's
been
so
trying to get
much
used to
better.
it.
Yeah, it's so much better.
It's nice. There are some problems that I still prefer the textbooks for.
Okay.
But
Yeah.
they
Once you
are-
get into it, yeah, you just never want to go
The
back.
only thing I don't like for the RPN is it's kind of annoying to do like 10 to the negative 19. Like if it's like, if you're trying to write something in and then picometers or something
Oh, okay.
like that, you know.
So you got 10, 19, negative, y to the, e to enter exponent. At least that's
And
how
you
mine
gotta
is.
start thinking in that order because
Yes. Yep.
you have to do things in the right order.
Right. I know. But then once you're sort of fully over there, yeah,
It works better.
that's cool. Question?
It's,
Got it? Are you guys done already? Oh, great. Pardon?
How many things are supposed to find?
All the yellow things. And then go ahead and do the test. Okay. So 3, 6, 7 yellow boxes. Yeah. Pardon? Okay. So you know standard deviation, right? It's just the square of that. So it's just before the square root sign. So so here, this variance, you take this minus the mean squared plus this minus the mean squared plus that minus the mean squared, add them up, and then divide by 2. Yeah, Thomas. Okay, the variance. I had a lot of questions. The variance is just the calculation for standard deviation without the square root sign. It's the thing before. So you've got the numerator is the sum of squares. Each data point minus the mean squared, added up, divided by 3 minus 1 is 2 in this case, right here. Because each of these has 2 degrees of freedom. Also, I'm going to add another yellow box. That's a new. I'll make it a trick new by that way. It's degrees of freedom. Does anyone not have the effect calculated? The number for the effect? So I'll type it out instead of copying over that. Negative 33.2. Pardon? Oh, this was just one data point. You have 2 others at the same run.
Okay, so what do those numbers correlate with like the temperature, pressure, and
Which?
okay, so like yield 1, 2, and 3, what are those telling you about like?
Okay. Yield 1, 2, 3 is, so for example, run 1, we set all these values at the low temperature. We did the experiment once and got this. We came back and did it again and got that. Did it again and got that. So that's why we average them together to say that's the average value at that condition. Good. question. Everybody get that sum product? The effect is negative 8.3. Okay. Get a variance of 21.5 there? That's huge. Anyone get that? No. What's that? All right. The variance part. Should we do it by hand? So variance would be this minus that squared plus that minus that squared. Whoops, did I miss a parentheses? Let me do that. So each number minus the mean, where am I, squared. All those added up, I can just do that. That's the sum of squares, but I want to take all that and divide by 2. That's the variance calculator. That's what your standard deviation button does on your calculator. You could have just did standard deviation and squared it, but really good to know that, right? Because that's telling you how far away from it is. Oh, there's more digits behind these guys. Yeah. That's true. So your numbers, results may vary. Okay. So now for this, I'm going to insert this. What really I ought to have is this degrees of freedom column, and say I've got 2 degrees of freedom at each of these locations. So I should take that times that. Great. Why are there 2 degrees of freedom associated with this variance? This variance came from 3 data points. So n minus 1. So 2 degrees of freedom for each experiment. So for a pooled variance, we take this times this, and we add up all those. And then we're going to divide that by how many? Divided by 16, or the sum of all those. Whoops. Sum of all those guys. So SP squared should be 28.6-ish. Did you guys get that? Square root of that is that. And then we have 2 times SP divided by, we can just put 24, square root of 24. SP is that. We've already done, I know it's 16, but I want to show you where it came from. So then this t value will be that effect divided by that noise. Negative 3.8. Get that about? The hurdle value, did that change after I messed with the data? T star is the same degrees of freedom, so forth. We'll do this over and over. We'll do this several times. Okay, we're going to go through this several more times. But you should at least have now a fighting chance to get the homework done. Yes? Put this on Blackboard? Sure.